Hello. Um, we're going to be continuing the Chapter 4 series for statistics in Harris Knight Edition Quantitative Chemical Analysis textbook. And in this chapter, we're going to be discussing 4.4, 4.8, just without the Excel part. So, just to kind of give a brief overview, we're going to be talking about t-test, we're going to be talking about Grubbs outlier, we're going to be talking about least square method, we're talking briefly about calibration curves and such. Okay, so let's get started. In 4.4, the book talks about t-test. So t-test is a statistical test used to see if two mean values are statistically different. Okay, so just take a note of the word here, statistically different. Just things to remember is that null hypothesis of t-test said that two sets of measurements come from population with the same population mean. Okay, and another thing to remember is that when you're rejecting a null hypothesis, if the phi value is less than 5%, meaning that the chance that the two sets of measurements come from the population is also within that same population mean. So in the book, they divided the t-test with three different cases with three different approach and with some three different formulas being used, but overall it's the same kind of I guess idea. So the first case is when you're comparing measured results with a given slash known value. In case two, we're going to compare values that you got after repeated sets of experiments. Case three happens when you're using a paired t-test when comparing individual differences. So for the first case. So in the first case, this occurs when you're comparing measured results with a given slash known value. So how to do it? So the first thing is that after you got the numbers, right? After you got the numbers from the data that you got from your experiment, you need to calculate the mean and standard deviation from your one var stat in your calculator or by hand using mean and standard deviation formula. If you're still stuck on it, I would suggest to um, go back into the previous video where I talk about in great detail the mean and standard deviation formula. All right, so the second step, we're going to compute the 95% confidence interval and see if that range includes the known answer. So in here at the top right, we're going to explain to you what confidence interval again. So remember, it varies depending on confidence interval that you're using because there's like a lot. We have a 90, we have 95%, such. Okay. So in this confidence interval, you have the x bar. X bar is right here. Oops. This one is known as x bar. So x bar in here is your sample mean. And then plus or minus after the x bar, which is this one. And then you have this ZC. So the ZC is your Z value. So Z value is just remember your standard, your data that you got from your experiment minus your mean divided by standard deviation. So after you do that, open parentheses, and then S remember is your standard deviation, and then you're gonna divide that by your square root of n. So n tells you how many are there in a data set. Okay, so basically you're gonna multiply your z value depending on what confidence level that you're in. So it depends. So it's different from each confidence interval that you have, and then you're gonna multiply that by s divided by square root of n. So after you do that, after you calculate it, then you're going to compare it with the confidence interval that you got from the table. In the book, they didn't, unfortunately, provide us with that table where you can compare on. So if the known answer is not within your 95% confidence interval, then the results do not agree. So in here, you're not really comparing whether it's statistically different or not, which case 2 and case 3 is going to be dealing with. Okay? All right. So case 2 is divided into two subsections. So the first one is when standard deviations are not statistically different. Right. Before we talk about the steps on how to deal with this one, we need to first talk about the formula. So in this one, right, you see this kind of complicated formula. So I'm gonna try my best to break it down for you. So this is an absolute value. So absolute value means that we are gonna make the negative into positive, okay? And then in here, inside of the absolute value bracket, you have x1 minus x2. So this x1 that has not, this one tells us that we are using the mean, okay, of the first set of data, and then we're going to subtract that, that's what it means, by the mean of the second set of data. Then we're going to divide that by S pooled. So what is S pooled? In here, you can kind of see this one, what this S pooled is. So S pooled, we're going to break it down again. So this is sigma. This kind of looking like inverted E, and set one. So this one is used when we're comparing two sets of data. Okay, that's why it's divided into two sets. So in the first set of data, what you're gonna do is that this sigma is technically the same as this one. Okay, so the first thing that you need to get is your standard deviation of your first set of data, and then you're going to square it. And then the n1 minus 1 here, this n1 tells you how many are there in your first set of data. So if you have 5 in your first set of data, your n1 would be 5, okay? And if your standard deviation of your first set of data is 6, then it's going to be 6, okay? After that, you're going to multiply after you subtract this part right here, okay? And after that, you're going to multiply it by your standard deviation. Okay, then this part. And then in your second set of data, you need to figure out your standard deviation. We're going to square it, kind of like what we did in this one. And then we're going to determine how many are there in your second set of data. Okay, then we're going to subtract that by 1. Then after you do that, you're going to multiply that back again into here. Divide that, that's what it means, n1 plus n2 minus 2. So the n1 once again is how many are there in your first set of data, plus n2, how many are there in your second set of data, minus 2, okay? And then this one right here is your square root sign. So just remember, you're going to square root after you calculated your that fractional component in your in this one, okay? Just remember that. And some things to know is when the t calculated is greater than your t table in the 95% confidence interval, that means the difference is significant. If the opposite happens, when we know that the difference is not significant, okay? So how to do the 2A case? So the first thing that you need to do is an F-test. So F-test, if so basically F-test is you're running a test to figure out whether your standard deviation is significantly different from one another. And the way you do F-test, remember, is the large standard deviation goes first on top, then divide that by the small standard deviation, which is on the bottom. So large standard deviation divided by small standard deviation. That's what f-test is. And there's like a rule there, once again, that you need to know, right? And that will tell you whether it is significantly different or not. And if it's significantly different from each other, then you can do this case. So we're going to calculate it using the formula given by first computing the S-fold, which already explained what it is, then using it in this formula right here, okay? And make sure when you're doing all of this math, whether it's calculated or by hand, you need to like put one more digit just for accuracy's sake. Okay, so just remember if your t-calc is less than your t-table, that means the difference is not significant. If your t-calc is greater than the t-table, then the difference is significant. All right, so case 2b. So this is when the standard deviation are significantly different. So same thing as case 2a. We're going to determine if the standard deviation is significant. We're going to run again an f-test. Okay? Just remember, if your f-test, right, which we're going to compare the f that we calculated by finding the standard deviation of your data set, do not differ significantly, meaning your f calculated is less than f table. That means they don't differ significantly. And then you use this formula. If the f calculated is greater than f table, then we use this formula right here. I know it looks very complicated, and we're going to try to explain it. And if it is, then you can do this case. And then we're going to calculate it using the formula given first by computing the S-pool, then that one again, okay? Make sure to retain one more digit in your answer. All right, so we're going to explain what this one is, okay? And so on your T calculated, which is the one that you're going to calculate, we have x1 and then x bar minus x2, then bar. So what that means is that, excuse me, I prefer using this way because it's kind of less complicated, and we're going to explain why. So in here, x1 in here is your mean for your first set of data minus your mean for your second set of data, and then you subtract that, and then you find its absolute value. Remember, absolute value, don't want any negative answer, so you're just going to take its positive answer. And then at the bottom, we have this complicated one. S1 squared divided by N1. So S1 in here, remember, is your standard deviation of your first set of data. Then you're going to square that. Then divide that by N1. So N1 in here is how many are there in your first set of data. And I would just put it there on the side. Then we're going to do the same thing for the S2. So we're going to find the standard deviation of your second set of data. Square it, divide it by how many are there on your second set of data. Then you add those two together, then you're going to square root it. Okay, and then what you're going to do after you square root it is that whatever you got from here, you're just going to divide that by this. Okay, I would just ignore the u1 squared because it looks complicated. And the u1 in here is just basically standard deviation. And then this one is special is because we're using a formula for degrees of freedom. Typically, degrees of freedom from what we have seen so far is as simple as n minus 1. But this one, since we're using a different case, we're using a different degrees of freedom, okay? And that is very important. So the S1 squared is your standard deviation of your first set of data, then you square that. then divide that by n1, so how many are there in your first set of data. And then here you have S2, 2 divided by n squared. So that one is how many, or this one is the standard deviation of your second data set, square it, divided by how many are there in your data set on your second one. Then you're going to square it. Okay, not square root, square it. Then divide that by this one again. So in here, I would first do this one first. So the standard deviation of your first set of data, square it, divide that by how many are there in your first data set, then you're going to square it. So whatever answer you got, I would just put it aside, divided by n1 minus 1. So the n1 is how many are there in your first data set. Okay, and then you're going to leave your answer here. So after you got the answer from this one and then this one, you're just going to divide that. Okay, and then you're doing the exact same thing in here. Okay, this is once again the standard deviation of your second data set. Then you're just going to square it, divide that by how many number or how many are there in your second data set. Then you're going to square it, leave it at the side. Then n2 minus 1, so how many are there in your second data set? Then subtract that by 1. So you're going to leave that one aside. And then you're going to calculate the top into the bottom. All right, so this is like the problem that is in the book. Um, so just remember, when you're doing two BKs, you need to make sure that the F test tells us that the standard deviations are significantly different before we even do this one, okay? In here, you need to calculate your T calculated and then your degrees of freedom. So T calculated again is what's given to you. So you just in here plug and chug pretty much, right? And then you do some math. So what they did is this is the this is technically the mass or the mean mass or average mass for the first set of data. Then this is the one for the second data. You just subtract that. You find its absolute value, so that's supposed to be positive. Leave that one aside, and then you're going to calculate this one first, right? So this is your first, this is your standard deviation of your first set of data. You square it, divide that by how many are in there. So there are 7 measurements according here. Okay. And then 0.001379. Remember, we leave one more digit for accuracy's sake. Okay. And then we're going to square it, then divide that by how many are in there. So in here it says there are 8 measurements. Okay. And what you're going to do is square root it. After you got the answer in here, we're going to leave that one here. Then what you're going to do is you're just going to divide what you got here by what you got here. A lot of people, when they're doing the math, they're not kind of careful and don't really do it slowly, and that's what led into a bunch of errors. So that's the reason why I broke it down like that. Okay. Then for the degrees of freedom, same thing. We're just plugging it in. The S1 squared, according here, is 0.0143. I'm going to plug that one in, then square it, divide that by 7, and because that's the N1, so that's the how many are there in your first set of data, you're doing the exact same thing in here, and then in here too, okay? Case 3. So case 3 is a paired t-test when comparing individual differences. So you're going to use a paired t-test when we are interested in the difference between two variables for the same subject. So the difference known as a DI is the difference between the two results for each sample. Then you're going to take the mean of differences. So remember, this is same method, same subject. That's the only reason why we're using paired t-test. So let me break it down again. So what you're going to do is you have your you have numbers in your data set. You're going to take the difference on those. And what you're going to do is that you're going to then, after you've taken all of those differences that is in your data set, you're going to take its mean. I know it's a lot of work, but you're going to take the mean of that difference. And what you're going to do, the di of this one is your first difference between your two values, okay? And then your second, then your third, right here, and then your fourth, then you're going to subtract that by the mean of your differences, okay? Then you're going to square it, okay? Then you're going to do it again for the second, third, and fourth, and then divide that by how many are there in your data set, which is your n, then minus 1, and then you're going to square root it to find its standard deviation. Then after that, unlike, running the F test, you really don't need to do it in here because all you need to do in here is um, find the difference of the mean, then find its absolute value. So that's supposed to be a positive answer, then divide that by standard deviation times it by square root of n. So square root of n is just the how many are there in your data set, then you square root it, then you multiply that, okay? And then in the next one, 4.5, they talk about Grubb's test for an outlier. So this is used to tell if one value is an outlier, meaning whether that one value is going further left, further right, and stuff like that. You really don't want that to be on one extreme over the other. And that's the reason why we're using a Grubbs test. So in a Grubbs test, what you're going to do is, once again, you have a questionable data. So questionable data in here is number that you think it's like very suspicious, okay? If you have a number that is very suspicious, you put it in that questionable data. Then you're going to subtract that by the mean of the data that you got. Then and then you're going to find its absolute value. So remember, absolute value, positive answer of when you subtract the questionable data into your mean, and then divide that by your standard deviation. So things to remember. If the G-calc is greater than your G table, then the questionable data should be discarded. Okay? Meaning you can just forget about it. If the G calc is less than G table, then the questionable data should not be discarded. That's the one that you should take into an account. Okay? And then the last one, we're going to talk about least square method. And usually what this one is used is to either linearize stuff that is nonlinear, or sometimes when we're doing calibration curve. That's the reason why we're using least square method. So least square method finds the best fit for a set of data points by minimizing the sum of the offsets or residuals of points from the plotted curve. It helps us getting a straight line. And like what I said, this is what you get when you're doing a calibration curve. So in here, you can think about it as line of best fit. I know this is done usually in like middle school or high school. So what they do is you draw the graph, and then you're gonna do some extrapolation and interpolation for it, right? To get the slope, get the equation. But in this one, I kind of made it simpler, so you really don't need to do that stuff. And in the book, they really talk about it not in a it's kind of talking about it in a much more mathematical way, linear algebra way, which some of you all don't really have that yet, and that's why I kind of do it algebraically here. So the first step, make a table. So on that table, you're going to label the table with x, y, x squared, x, y. And then what you're going to do is add all of your x values, add all of your y values, add all of your x squared values, and then add all of your xy values. Then you're going to use these formulas to create the line of best fit. In the line of best fit, we're going to use the linear equation, which is y equals mx plus b. Now, this is not the same as those extrapolation and interpolation that I was talking about, where you draw like a triangle to figure out the slope. Now, we're not going to do it this one. Instead, we're just going to use this one, okay? Okay, then you have m. M is equals to n sigma xy, n minus sigma x, sigma xy, divided by n sigma x squared minus sigma x, then squared. Just be careful of that. That's not the same thing. And then b is equals to sigma y minus m sigma x divided by n. So what the heck is sigma? So sigma means you're adding. Okay, so that's the reason why we're adding all of this x, we're adding all of this y, adding all of our x squared, adding all of our xy to get that, okay? Okay, that's about it for this one. Thank you so much.